Hello. Let us consider some kind of system of laser that is projecting energy towards a SAO. And this SAO is reflective and it's being pushed by the photons in the laser, perhaps off towards an interstellar journey. And we're going to consider something that's similar to a Starshot-like probe. So Starshot was a gram scale probe, meaning that it was to have a total mass of order 1 gram, which is 10 to the minus 3 kilograms. And we're going to assume a moderate reflectivity of mu equals 0.7. Now for Starshot, we know that the velocity to be achieved was something like 20% of the speed of light, which is around 60,000 kilometers per second. And if we assume the burn time for the laser pushing the SAO was around 2 minutes, that is 2 times 60, which is 120 seconds. And first of all, we need to obtain the acceleration for this. So we know from very simple kinematic relationships that velocity is acceleration times time. So we're not looking at relativity here. Therefore, acceleration is velocity over time, which gives us 60,000 meters per second divided by 120 seconds, which is equal to 500,000 meters per second squared. And we know that 1g is equal to 9.81 meters per second squared. Therefore 500,000 meters per second squared and divided by 1g gives us around 50,968 Gs. So this is an enormous acceleration. We can approximate that as around 51,000 Gs. And so now we're going to work out the power requirement of the SAO, or the power is simply given by the mass times the speed of light times the acceleration divided by 2 times the reflectivity, which is 10 to the minus 3 kilograms, times by c, which is around 300,000 kilometers per second, times by our acceleration, which is 500,000 meters per second squared, all divided by 2 times 0.7, and this gives us a power of around 1.0707 times by 10 to the 11 watts, which is also equal to around 107 gigawatts. And this explains why for Project Starshot they were talking about a requirement of around 100 gigawatts. And we can also calculate what the distance would be under the acceleration, assuming non-relativistic. We can approximate that as s is equal to a half at squared, which is 1/2 500,000 meters per second times by 120 seconds, which is our 2 minutes squared, and this comes out as 3.6 times by 10 to the 9 meters. And we know that 1 AU, the mean distance between the Earth and the Sun, is around 1.496 times by 10 to the 11 meters. And so if we divide that, we simply get 3.6 times by 10 to the 9 meters divided by 1.496 times by 10 to the 11 meters, and this gives us around 0.024 astronomical units. To put this into context, the distance to the Moon from the Earth, the mean distance is around 384,400 kilometers, and this is around, if you do the maths, 0.00257 AU. And so if we work out the difference between those two numbers, 0.024 divided by 0.00257, we get a number of around 9.34. In other words, the probe, when it's accelerating for 2 minutes, will have gone to a distance of approximately 9 times the Earth-Moon distance under acceleration. And also, we want to work out the energy equivalence on the SAO, which is simply given by the power, which is in watts or joules per second, multiplied by the acceleration time, and that is 1.0707 times by 10 to 11 joules per second times by 120 seconds, and this comes out as 1.2848 times by 10 to the 13 joules, or around 12.848 terajoules of energy. That's how much energy is required to be delivered to the SAO over its boost phase. So just to recap, we have a spacecraft with a mass of 1 gram. We have a SAO reflectivity 0.7. We have a velocity of around 0.2 c, 20% speed of light. We've got an acceleration time of around 2 minutes. We've got an acceleration requirement of around 51,000 Gs. We've got a power requirement of 107 gigawatts, and we have an energy requirement of around 12.85 terajoules. So this allows us to start to sketch out a SAO design of this kind of system, which would typically be perhaps a square SAO along these lines, and the spacecraft will be embedded and integrated into the SAO structure, and perhaps some sort of maneuvering on the corners, and this would only be around 3 to 4 meters in size. So this is quite a small size scale that you have to hit from a ground-based laser or from one in Earth orbit. And the other thing we can look at is the cost for the lasers, and with today's technology we're looking at something like $100 per watt of laser power. So we multiply this by our laser power we calculated, 1.07 times by 10 to 11 watts, and this comes out as 1.07 times by 10 to the 13 dollars, or $10,707 billion, or around 10.7 trillion. Not cheap. The aim with something like Starshot, which would perhaps be possible in 2 to 3 decades, is that the cost will come down to something like 10 cents per watt, which, if we multiply this by our laser power, once again, it comes out at 1.07 10 to the 10 dollars, which is equal to around 10.7 billion. And this would kind of be the goal for a project like Starshot. This is where it starts to become affordable. Ultimately, in the long term, perhaps in 50 years or 100 years, if we could bring the cost of the laser down to something really cheap, like 1 cent per watt, then multiplying that again by our laser power, we would end up with 1.07 10 to the 9 dollars, which is around 1 billion. This would be the ultimate goal. At the moment, this is science fiction. This is reality, and this is the vision. That's it.